All right. So we're going to change our subject. We spoke about stars, all about stars, and for the rest of the course, we're going to speak about galaxies. Here is a gorgeous galaxy, just a funny-looking galaxy. This was taken by the Hubble Space Telescope, and it shows, actually this stream goes down a ways. There is more stuff on this thing, and the object is harassed. This object is not as simple as a star. Stars are born, they have a size distribution, and that size tells us everything about the star. It goes through its life the way we talked about, but the galaxies are individual. There is nothing about a galaxy that is unique. Every galaxy is different. They have different sizes, different light, different brightness, and it doesn't have these simple rules for making them making them simple to understand. Now, this galaxy, you note, this galaxy is taken in a field, just taken a random field. Look at these things behind it. You know, those are smaller little galaxies. They're not just little dwarfs surrounding this guy. They're back behind it. It's the background of galaxies behind all the foreground galaxies we see. The galaxies go on and on and on and on forever. And we want to study that question. What do they say? All right, galaxies are funny. They're a little bit squirrely, like this guy, or they are sometimes gorgeous. This is a beautiful Hubble picture of a galaxy known as M104, the 104th object in a catalog of objects not to be confused with comets. This was the catalog.
See, somebody's supposed to be changing this. It's not your fault. It's students coming here doing this. It's not. Okay, try it.
All right, fine. All right? Yeah. Okay. Yeah, that's better. Okay. So you note what he sees, that the distance from the Earth and the velocity from the Earth seem to be more or less following this line. So let's do some more. He looks at other galaxies. Going around. Let's do, all right, that's all in the southern hemisphere. One more here. Then he goes over here and does the northern hemisphere. Blah, blah. Measures them, measures, and he says, gee, wow, look at this data. He had no idea what to expect. But he saw that as a function of the distance, that is how bright the Cepheids are, the galaxies are further away. The objects with the faintest Cepheids are the furthest. And he draws a line through it. Show a plot. All right, this line says that the velocity of recession is proportional to the distance of the object. This is known as Hubble's law. This line is known as Hubble's law, and we'll see this line as we go on. What does this mean? Every galaxy is more or less moving away from us. And Hubble's discovered this in the 1920s. Now, at the time it was discovered, nobody had any idea about this. Nobody thought about what the universe is doing. The people more or less assumed that the universe is static. That's what Newton had assumed, and that's what Einstein assumed. Einstein assumed the universe is static. Why not? It's static. It's here. It's the same now. It was yesterday. Should be static. But Hubble said, no, it's not static. The universe is definitely expanding. That means that in the past, these objects were close to us. In the future, they're going to be far away from us. The universe is definitely expanding. And when Einstein heard this, he said, oh my God, what did I do? I have screwed up the theory of relativity, because he didn't take that into account. Okay, he of course didn't know about it, and he should have, if he had realized it, he would have had the most amazing discovery. But we'll talk about that in a minute. All right. Okay, Hubble supplied the distances, and he used the Cepheids. All right, so he measured the distances to every galaxy, and then measured the spectra of the galaxies and measured the velocity of them as well. All right, now Humason was a mule driver who worked with Hubble at the telescope. This is all occurred outside of Los Angeles on the observatory using, they have a 100-inch telescope there, a beautiful, magnificent telescope that was built about that time. And with it, they made these fantastic discoveries. To get up there on a mule train took, I guess, most of the day. But the man did it. He drove the mules, and when he got tired of that, he became an observer. Okay. Now, the plot was a straight line. The further away the galaxy, the faster it was moving away from us. The velocity increased linearly with the distance in this form. Velocity of recession, as measured by the Doppler shift, is equal to h naught times d. D is a distance. H naught is a constant that astronomers now call the Hubble constant. H naught, this means Hubble constant today. It doesn't mean the H sub 0 means today. All right. Now, the units of this are a little strange. This is kilometers per second. This is kilometers. Okay, but this is measured in megaparsecs, and this is in kilometers per second. So to make it right, kilometers per second per megaparsec is the units of h naught. You note the kilometers and megaparsec are both units of distance, so they cancel. And Hubble's constant varies as 1 over time. 1 over time is the age of the universe. The age of the universe in this case turns out to be 10 billion years. Just from the Hubble constant, you can learn how old the universe is. All right. Now, what actually happens in the universe? Here's the way you should think about it. Imagine the universe is a two-dimensional object, and it's existing on a three-dimensional sheet. Here's the balloon. The galaxies are A, B, C, D. At one time, they're expanded this much, and at a later time, you blow the balloon up, and A, B, C, D are now further away. They all are further away from each other. Where is the center of this balloon? Well, on the two-dimensional surface, which you should think of as the analogy of our universe, which is a three-dimensional surface, in our three-dimensional surface, there is no center. Like in this case, where's the center of the balloon? Well, you could say in the middle of the balloon, but that's not right. The center of the balloon, you have to be on the point. Is this point it? That point? Another point? Is it down here? They're all the same. They're all equivalent. Everything is the center. The reality is, this is a simplification. You should look at it as the real universe is a three-dimensional case. All right, now, galaxies are a letter painted onto this balloon. Each one the same. The expansion of the universe appears to be the same in all directions, and that's what we call isotropic. The same in all directions means it is isotropic. All right, and everybody thinks that they're at the center of the universe and the Hubble flow is centered on them. Everybody sees the galaxies moving away proportional to their distance, proportional to their velocity is just exactly proportional to their distance. All right, then in this case, the correct analysis is that there is no center to this balloon. Like on the Earth, where is the center of the Earth? I mean, where is the center of everything? Well, obviously, the center of the Earth is not someplace you go to. Center of the Earth is in the middle. It's hot there. The center of the Earth is, I don't know, wherever you want it to be. London, San Francisco, they're equal centers, but they're all equal. All right, there's no center on the balloon. That is the important issue. It's a two-dimensional surface embedded in three space. The reality is you have to think of our three-dimensional surface embedded in four space. Embedded means that I can place the two-dimensional surface of that balloon easily in a three-dimensional sphere. There's no problem doing that. We're all used to that. What is harder for you to do is to imagine our three-dimensional surface of a balloon is wrapped around a four-dimensional space-time, a four-dimensional sphere, and that's the reality. Understand? Pretty easy? Not so easy? You have to be confused at this point, if otherwise you're not paying attention. Yes?
I think we read an article on Universe Today, something about there's no center in the universe. Like you might infer that how the projectiles fly around in the universe,
Yeah.
and then you try to find the hottest spots in the universe, that would be the center. But then actually there is no center.
There's no center in the universe. That's absolutely right. And that's the key you have to understand from this. No center at all. This is absolutely the way relativity will do it. Einstein's relativity theory is perfectly capable of describing the universe. This is something he did not work on much, but when he had the theory written down, people realized that it easily describes the entire universe, and we will use it for the rest of the course. Okay, now the issue with what happens to wavelengths. I said that we looked at a galaxy and the galaxy is redshifted. Redshifted means that the lines have all been shifted to the red. They've been shifted longer. They're red. Is longer wavelengths. Now that means that you can think of it as the following way. That you put on a balloon, you draw a swiggle of a balloon on a square, on a pattern, and then you blow the balloon up. Blowing the balloon up makes the pattern bigger. These are short waves, these are long waves. What this is the wavelength of light. If you have light here compared to here, the wavelength here is longer. That is how you should think of the redshifts we see from distant galaxies. The galaxy is not flying away from us. That is not right at all. The galaxy is sitting still on the expanding balloon. But his photons are emitted from the galaxy, and once emitted, they're on the balloon. The balloon expands, and the redshifts, those photons are expanded. Every photon is expanded. So the photons from something far away take a while to get here, and in the meantime, the universe expands, and the universe, makes the photons become redder and redder. That is why Hubble saw the photons were stretched to longer wavelengths as he measured their distances. All right, so this is a simple version of what is going on in the universe. Okay, this is redshifting. The space is expanding, but the particles are not moving. It is expanding space. And that's very important to remember, because we're going to make the space do really weird stuff in the next week. All right, now, Cepheids are the distance indicator that Hubble used, because Cepheids were fairly common, and he could see them pretty far. They're pretty bright. But supernovae are a much better indicator than Cepheids, because you can see them to tremendous distance. All right, let me see how we can get that. Okay, so here's a galaxy. All right, and bang, up goes a supernova. And a supernova leaves a very bright spot for a while. It peaks up at, what is that? Apparent brightness, magnitudes per kiloparsec squared. All right, this tells you how bright it is, and it goes up and goes down over a 50-day period. And that is what is seen and if you look at the distant sky, you can see that. Now, because we know how bright each supernova is, then we can tell from the apparent brightness how far away it is. And that type of work is going on here at Berkeley. It's a big deal here in Berkeley. All right, so that is the way you measure the brightness of a supernova. Okay. All right. They obey the Hubble's law, and we then measure how far away it is, and you can get a calibration of Hubble's constant when you do that. You obtain accurate values of Hubble's constant, and you measure these supernova to pretty large distances. The issue of using the white dwarf supernova, which are the type of supernova, first type I spoke about, that's the type where the white dwarf is accepting material from another star, raining onto it, and then the white dwarf flashes, and it burns for a bit, and that's the type of supernova particularly they're looking for. These supernovae are 10 billion they're as bright as the entire galaxy. 10 billion times as bright as the sun. All right, these don't happen very often, but people look for them. And when they look for them, they find them. All right, so they are calibrated with galaxies that have Cepheids. They can observe to very, very far away. And they're all the same peak luminosity, more or less. And that is what we use to measure the distances of the galaxies. This work has been done at Berkeley, and a lot of prize. In fact, a Nobel Prize was given in the last few years, just this last time, was given for this type of work. And we'll talk about this a little further as we go on. All right. Now you've got to be lucky to observing a galaxy when it explodes. And they're not lucky anymore. They do it by hard work. You take a lot of photographic plates and you look at these regions, thousands and thousands of galaxies, night after night, and then occasionally you see a supernova going off. That is the trick. Okay, now what you learn is the expanding universes. Now let me talk about this a little bit. Okay, so let's look at our universe. So the universe the universe expands. That much we saw from the local data. So let's look at it. All right, the universe is a bunch of galaxies all expanding. That's one way to look at it. But that picture requires you to have an idea what the universe was when it was condensed. Was it a hot knot? Were all the galaxies pressing on each other? Were they as condensed as it appeared on that picture? Well, let's try another expansion. All right, let's try this. Let us say that instead we just had the galaxies are lying on a grid, a two-dimensional grid, and the grid expands. So this is a set of grid points. You turn it on, and the grid expands. As the grid expands, the galaxies are pulled apart. Which is the right way to think about the universe? This is the right way. Think of it as the grid. The grid spacing was small, and now it's become large. All right? It was small, and now it's become large. All right. And you can say, well, all right, let us ask, what is the distance between these objects? We'll say the center of the universe is E, and he wants to know what the distance is from every galaxy around it. And so you measure the distance to all those galaxies, and they're at different distances initially. You measure their velocity of recession and the final distance, and they all give they all fit the Hubble law. All right? If you move the center of the coordinates to position A instead of position E, you could do it again, and you'll find the same answer. The distances are directly proportional to the velocities, and that is the issue. So it doesn't matter which galaxy you take as your center. All the galaxies see exactly the same thing. All right. All right, the galaxies are moving away from us. They're swarming out. The Milky Way looks like it's at the center, but it is not at the center. That's the first thing you learn, even though the expansion appears to be isotropic from our point of view. We're not at the center. We are not anything. Now, in an issue, we are taking the Copernican viewpoint. Copernicus said, well, the Earth isn't the center of the universe. All right, and branching out, let's now say again, the Earth isn't the center, we aren't the center of the Milky Way, and the Milky Way is not the center of the universe either. That's what he means by this, to take the Copernican viewpoint. We're not the center of anything. We're just a typical galaxy out of millions and millions of millions of galaxies that we see around us. Just a run-of-the-mill galaxy. All right. The universe is expanding. Galaxies expand with it, and there's no center or edge to the universe. These are the lessons. Every galaxy looks exactly the same. That is the idea of a Copernican viewpoint. We don't think we're special. We think we see something that is characteristic of everything else. All right, now how does this work? If you look at the expanding universe, you can tell, and you measure H0, the way we did at the beginning, then that tells you the age of the universe. It tells you when they're together. If you run the clock backward, then you can tell when the galaxies will collide just by the expansion rate now. And when you do that, they're going to collide basically at a time 1 over h0. This has units of inverse time, so inverse of it gives time. How long the universe took to expand to its present size. And if the expansion rate was constant, that would measure the age of the universe. And that age is the best estimate of h0 is 71 kilometers per second per megaparsec. That is a value that gives us an age of the universe 13.7 billion years. The age of 13.7 billion years was not picked out of a random hat. If you hear people talk about that, it's not a random number. It is the inverse of the Hubble constant. And that tells you how old the universe is. So the question is, why is it 13.7 billion years? And some people will say, well, wait a minute, what happened in 13.8 billion years? What was the universe like just before it blew up, before the expansion began? Anybody ever worry about that? Okay? Yeah. Well, what happened? What do we mean about the universe began? Clocks began at that time. How can we talk about such a crazy thing? And the issue is, this is real. These questions are absolutely real. And they have an answer. And I'm going to try to give you the answer. You're not going to believe it, but I'm going to give you the answer in the remaining lectures of this course. The cosmology, as witnessed from this sort of stuff, is mind-bending. It is totally amazing. All right, for example, let us look back at an object. Here we've got a system that shows space going this way and time going that way. This is a simple space-time diagram. All right, so one coordinate of space is this way and time is that way. Now, here is let's go back 400 million years. And this is us. We go up here, go up and up and up. So here's us today. Here is another galaxy over there. And he's, I don't know, some distance away from us. Now, 400 million years ago, we'll say this guy emitted photons, and the photons traveled. They aren't fixed in space-time. They move in space-time. They move, and in the meantime, this guy has moved apart from us. This is the Hubble expansion. In the 400 million years, he moved from here to here. All right, so we look at him. We look back in the past as we look at that galaxy, and we see him right here. 400 million years ago, he was there. Okay, that is the look-back time. All right, the speed of light is finite. It takes a while for light to travel. It took 400 million years for photons to travel from here to here. And that's the look-back time to that point, 400 billion years. That's how long it took to get there. The further out in the universe we look, the further back in time we see. Of course, that is familiar to us all. If we look at the sun, we see the sun as it was 8 minutes ago. If we look at Jupiter, we see it as it was half an hour ago. If we look at a star, it's typically a few years light travel time. If we look at a supernova remnant, we can say Kepler saw a supernova remnant, or whenever year or Brahe saw a supernova remnant in whatever year it was. Well, that means that was the time the photons arrived for him to see it. But of course, the supernova remnant really occurred much earlier. And the same is true in cosmology. We're talking about galaxies now. Remember, I said the nearest galaxy is M31. That's a nearby galaxy. It's about as big as the Milky Way. And its light travel time is 2 million years. Okay? A flash goes off, and we don't know anything about it until 2 million years has passed. Is that a long time or not? Well, you've got to compare it to the age of the universe. The age of the universe is 13 billion years. All right? A billion years is 1,000 times a million. 13 is, so it's 6,000 times longer or so. Is that right? 6,000, 13, yeah. 6,500 times longer. So the age of the universe is, compared to the time it takes the light to move from Andromeda to us, that's nothing. It's small compared to the age of the universe. So don't worry about it. But if you want to worry about something, worry about the galaxy so far away from us that we can't see it except when its light travel time is measured in billions of years. It's far enough away that it took half the age of the universe for the light to reach us. That is pretty impressive. And what does that say? Well, that says if we see in the past, we look at these galaxies and we see them as they were. We don't see it as it is now. We see it as it was 6 billion years ago, or 8 billion, or 10 billion years ago. We get a chance to look in the past by looking at telescopes. That's what's so magical. I look in the past every night I stare at the telescope. And astronomers are used to that, and they talk about these galaxies so far away, it's mind-bending. But that is what we do. All right. So you look back in time and you see these galaxies. At vast distances, we have long look-back times. And so we really don't talk about the distance between us and another galaxy. It's not as convenient as to talk about the light travel time. That is what we actually see. The light travel time to Andromeda, 2 million years. The light travel time to this galaxy, 400 million years. That's the way we characterize the object. The light travel time to the galaxies I've looked at, 10 billion years. 10 billion years the photons have been traveling. That's pretty impressive, yes?
Why does it make more sense to use look back time?
It is because the distance does not refer to something you can actually measure. Either way, whatever you want. All right, it doesn't really matter. Okay? You just have to understand what I'm talking about. Okay? All right. The distance to the galaxy. You can say it's the distance when the photons were emitted or the distance when they were received. And you can, whatever you want. Doesn't matter. But you have to understand that it is changing with time. All right, there's no ambiguity. It took this long, 400 billion years, 400 million years for the photons to travel. So in that sense, use that number. The light travel time is a real number that you really measure. Okay. Now, what is the size of the observable universe? Okay. The universe has no edge. But it does have a horizon. The horizon is the furthest you can see, the furthest the photon will travel in the time of the universe. There is some place that emitted photons to us 13.7 billion years ago, when the universe just began. Right? And we can see that. But we can't see an object that's further away. So that sense, that is a cosmological horizon where the look-back time equals the age of the universe. So what does it mean? What I'm saying is the following. Okay, let us say we're here and we want to draw a circle. A circle is this distance. And this time, this distance L has a light travel time. Light travel is 13.6 billion, 13.7 billion years. That is to say, a point here emits a photon to us, and it takes the entire age of the universe to get to us. That means that a point out here emits a photon, and it's going to take longer than the age of the universe to get to us. Therefore, we don't see it. We don't see it at all. Never. So this is our cosmic horizon. There can be the universe extending very far away, but we've never seen it. Now, if you want to see it, you just wait around. If you wait 13.7 billion years and you wait 100 million years, the circle will be bigger a little bit, and the galaxies in here will become visible to you. That means you can see them at the time when the universe was between the age of one and the age of the other. You see them at a time. All right? So think of it this way. Here, close in, you're seeing the galaxies at a certain age, at a high age. Here, you see them at a younger age, younger. Out here, they're younger, until you get so far away, you're looking at them when they were born. And that's how far you can see. See to the beginning. All right? Now, that is basically the basic idea of cosmology. What are we trying to see? Okay, now, for the rest of the talk, I'm going to change topics right now. We're going to come back to cosmology and talk about it at length. But here I want to talk about centers of galaxies. Centers of galaxies hold these gigantic black holes. What in the world are they doing in there? Why does this huge black hole exist in the center of the galaxies? And this week's problem set, which I'm handing out today, is a problem involving timing of the galaxies around Sagittarius A star. Here is the position of a star measured over a 10-year period. And they've now completed the data. It goes beyond 2002. They've seen the data, and it goes all the way around. Is moving all the way around. You're going to use that to estimate the mass of M82. The mass of Sagittarius A star. That's one of the problems, and that's a good problem for you. I'll show you how to do that. Okay. Now, fast-moving stars, you make these measurements in the infrared, and you use Kepler's law, and you're going to infer a mass of 2.6 million times that of the sun for this object in the center of the center of the galaxy. That is the mass of the black hole in our galaxy. Why is it there? What other evidence do we have it exists? What can be so small yet so massive? And the answer is the only thing that can do it is a black hole. We've tried everything else, and nothing else will do it. For example, we saw this case. Here is a black hole here, and we know that's a black hole because on the front, on one point, there's a disk in here, and the emission line shows rapidly exceeding material, rapidly receding material, and approaching material, just rotating around like a disk should be. And that gave a gigantic mass. It's just like the solar system, and you find 10 to the 9th solar masses. A huge amount of mass on one galaxy. All right, now, this all is related to the subject of quasars. Quasars are sometimes known as QSOs, quasi-stellar objects. Quasars were discovered in the 1960s. And for a while, people couldn't believe what they saw. They were quite amazing. Here's some of the data. All right. They saw these radio sources in the 50s. Astronomers could not identify them. They weren't sure what was going on. The radio telescopes were not very good. It was hard to determine them. But a few of them with these names, they look blue and they look star-like. Blue star-like objects seen in high latitude. Are they stars? No. They were not stars. When the blue stars were taken, the spectrum was totally bizarre. The spectrum didn't recognize anything. People were not expecting it to be anything, or they didn't know what it was. And they finally got a spectrum, and somebody, Martin Schmidt, identified in 1963, he identified an object at a very high redshift, huge. This was at the time considered to be gigantic. The Doppler shift was 16%. So the thing must be far away if it's got that kind of Doppler shift, but it made no sense. How could something be so bright and so blue and so far away? What was this thing? People didn't suspect anything at all. What were they? We've now pushed it out to redshift 6. All right, this means that the redshift is what that means is that the objects are not moving faster than the speed of light. What am I saying? You learned a little bit about the Doppler shift, that the lambda shift over lambda was equal to V over C. This is something we saw for the study of stars in our galaxy. The stars are moving a little bit, and this is the simplest Doppler shift. Here, we see objects that are, this is actually what we call Z. It is delta lambda over lambda, and it's a number like 5. If I see a number like 5, what the hell does that mean? 6 up there. That means velocity is actually 6 times the speed of light? No. It means that this formula does not work anymore. The reality is the object is very far away, and there is definitely moving fast, but is not moving faster than the speed of light. Okay, and these things are gigantically luminous. Now, what is it? How does it get there? Okay, the further away we are, the further back we look in time. Quasars apparently are a phenomena that is not very common now, but was a phenomena of galaxies that was very common in the past. There aren't any quasars near us, but they are seen at great distance. And let me show you what I mean. Here, for example, is the first spectrum that was seen. They couldn't tell anything. The comparison spectra and other lines. This is just a comparison lamp. And here's a line. They didn't know what the hell this was, and they stared at it for a long, long time. Nowadays, we see spectra of quasars that are very strange. They extend through the X-rays, ultraviolet. They have bumps here, and they're sometimes weak, other times strong in the radio. Very broad band emitters. Here's the optical band. We didn't know what this was. It doesn't look like a star. It's huge. It's not a star. Stars don't look like that. Stars don't have emission lines that are that broad. Very strange. Okay, star-like object. Spectra doesn't look anything like a star. Star-like object in that it looked like a star, just they couldn't see anything. And they're not, the objects emit wavelengths everywhere. Quasars. But they turn out to be incredibly luminous, 1,000 times brighter than the entire Milky Way galaxy. And they're very compact. How can an object be so compact and luminous? What can it be? these quasars, and they fluctuate in a few years. The whole thing, it would be bright, then faint, and bright and faint. If the object fluctuates in a period of a week, say a year, suppose the object fluctuates in a period of years, a year, then it must have a size that's smaller than a few years across. Because otherwise, how does it manage to do this? If it does fluctuate rapidly, then it has to be compact because the light has to travel from one side to the other. How can an object be so much brighter and change its luminosity by a factor of 2 in such a short time? How can this happen? And this was a tremendous mystery in the 1960s. Okay, so all this meant that the quasars, whatever they were extremely compact. Very, very compact. And very high, they're very far from us because of their high redshifts. Okay, here was a picture of a few. They weren't sure what they were. Here's a picture of galaxies that have quasars in them. And this picture's, here's the quasar, the very hot spot. But all the galaxies have fuzz around them. At the time they took this picture in the early 90s, they still weren't sure that the quasars were in galaxies. The quasars could have been anything. They didn't know what they were. But here was something that showed the quasars are, in fact, part of galaxies. The galaxy is this emission on the outside, but the quasar is in the center. They are active galactic nuclei, AGN. That's what we now call quasars. Active galactic nuclei. What's going on? All right. Here is amazing. This is an amazing picture. This is a picture. Here's a galaxy core. This is an entire galaxy. The galaxy, this distance from here to here is much bigger than the size of a galaxy. A galaxy is 10 kiloparsecs in size. This will be 10 megaparsecs in size. The galaxy is a small little spot. It's down there. And yet it has a gigantic spot here. What is this double radio source? And this is something that they saw in the 50s. This is all radio emissions shown here. How can it do that? Radio galaxies, they emit huge amounts of radio waves here and here, and yet it all comes out of a tiny core. What can do this? All right, they come on either side. They're not the galaxies that emit it. It's the radio lobes that seem to be emitting these things. What are these things? All right, these radio lobes are gigantic. They're huge compared to the size of the galaxy itself. And these are jets. These are jets sent out by the central black hole at the center of that galaxy that is making the AGN. This was an incredible surprise to discover this. Here, for example, is another one. Here is this galaxy is one that is, the AGN is right there, and it emits in the blue. Those are X-rays in the blue. Radio is red. Very broadband emission seen in this sort of picture. This is, these are incredible objects. Here's another object. Here's a galaxy here, and it blows out two jets, but the galaxy is moving this way. It's moving, and these jets are pulled back because it's moving in a medium of hot gas around it and makes these jets move. So they, all right, they're swept back because the galaxy is moving through intergalactic medium. Gorgeous picture. A nearby galaxy. Those are some of the radio lobes. All right, here is the core of M87. This guy, we've measured this mass of this thing, and this thing weighs 10 to the 9th solar masses right there at this point. It is a synchrotron. This is an active galactic nuclei. And it emits these radio waves. It's not cold gas and shoots out a jet. The process of emission is called synchrotron. It's emitted by charged particles spiraling around magnetic fields. And that's what makes this radiation here. And the question is, why does this galaxy have this incredible emission? What does this mean? What is going on? Here are pictures close in. Here's Hubble picture. This is of another galaxy. Gigantic objects. And here is a jets coming out. Here is a blow-up of it. And it shows a disk and a little hot spot in the middle. That is an idea of what is happening on these objects. What are they? Well, these active galactic nuclei, we think we understand them. They are gigantic black holes in the center, and they have accretion material around them. Remember, the accretion ring is the ring that forms around an object. It turns into planets. It's the junk that just spirals into the galaxy or star. And this accretion ring gets really, really hot. For one galaxy, you measure a mass. For M87, you measure bigger mass. And it is rotating around, and it apparently can make a jet coming up this way and that way at its rotation axis, north and south pole. All right? These are incredible objects. They are the centers of these galaxies. All right, so the matter is swirling through this disk, and it goes through an event horizon, a horizon. We'll talk about that a little bit. All right, and the gravitational potential lost. How much gravity is lost? You know, we've talked about the potential energy that in various objects. And we said in quasars, or for neutron stars, you could get out as much as 10% of the mass was available, because the potential well was basically 10% depth. Quasars are related to active galactic nuclei, and they have deeper potential wells. So it's the same idea, potential well that is quite substantial, and material can get in quite close to it. And of the rest mass energy of this material as it falls in, we think that the amount that's radiated away is somewhere between 10 and 40% as it spirals down to the center of this black hole. 10 and 40% is a huge amount of energy. Remember that these things were, the mass of this thing is already of order 10 to the 9th solar masses. It's stunningly large. These things are incredible generators of energy. And if you want a lot of energy, the way to do it is black holes. Black holes accreting material shine, and they will make incredible mess. Here is the idea. A black hole right there accretes material around it, and the material has embedded in it magnetic fields. The magnetic fields get wound up tighter and tighter, and they eventually make a jet, and it shoots out in one direction, or these two directions, the poles. As it rotates, the material then rotates down into the center. And it gives, this thing is hot, really hot, and shining at us. What you see is the heat given off by the accretion disk. You don't see the black hole directly, but you see the accreting material around it. Amazing amount of luminosity gives off. And remember, our galaxy had one of 10 to the 6 solar masses in the center of the galaxy. It's not active now, probably because there's no accretion onto it now. It has cleaned out everything that would fall onto it and is waiting for the next victim. If you want to fall into this black hole, you'll shine. A bright light will shine as you ripped apart. But if it might be a quasar at some level if you really get ripped up. Okay, the formation of the jets, the magnetic fields get twisted, pulled out to the disk, accelerated like a slingshot. Particles shoot out at incredible speeds. These are amazing engines, and it happens all the time. All right, so you see a quasar, if it's pointing at us directly, you see a quasar. Depending on the orientation, you could see the radio galaxy, you see the jets or not. Depending on how the orientation of this object is relative to us. And we'll change what we see. All right, so the lobes are the jets come way out, shoot very far away, and make the incredible fireworks of the intergalactic medium. Now, here's something that is very, very mysterious, and this is a current problem of research. I'm going to show you what this is. I'm plotting here the following. As a function of the velocity dispersion and the mass of the black hole in solar masses, 10 to the 8th, 10 to the 9th, 10 to the 7th, the velocity dispersion seems to go up. Now, velocity dispersion means the speed with which the stars are moving in the galaxy. For reasons unknown, when the velocity dispersion is high, the mass is high. Nice. This is a good linear plot. This is for real galaxies and real objects. We don't know what makes this. Not only is this correlation seen between the velocity dispersion and the mass, but a correlation is seen between the mass of the luminosity of the bulge. You plot the luminosity of the bulge in terms of solar luminosities. Here, 10 to the 9th, 10 to the 10th, 10 to the 11th. And you plot the mass, and again, it's a linear curve. A linear curve is not the best fit, but it's still a good fit. All right, what does that mean? We don't know how to explain this. This is currently a problem. People would like to understand it, but it is a problem. We don't know how to explain this. But it is an object. It is something that people try to work on. When we understand better, we'll understand more how the quasars formed, what they had to do with the formation of the bulge. But that's the mystery. And this was something completely unexpected found with when they were looking at distant galaxies. You find these incredible quasars out there. And they're an event that happened during galaxy formation. So as we go on, we're not going to talk about quasars anymore, but we will go back to galaxies in the expanding universe. But we saw these incredible objects right there, and they are common in galaxies. Okay, I think that is the last lecture. Yes. Okay. On Tuesday, we're going to speak more of the expanding universe, and we will speak about the distribution of matter in space on big scales. We're getting closer to the work that I've done, so this is something that I've worked on. I have a number of papers on this, and If anybody wants to read them, I could tell you where they are. But, yeah. Oh, by the way, that article I gave you a reference to was the article that talked about 3 separate crises where scientists came in for a lot of talking that was bad, that people didn't like what they had said and didn't like the idea. They didn't like the heliocentric cosmology. They didn't like anything. They didn't like Einstein's theory. They thought it was too crazy. They didn't like. They don't like the idea of the Earth getting too warm. But they're about equal position. So read his article and see. I look upon it as an adventure. We're going to see the Earth going back to the age of the dinosaurs. Right on. That's what we're doing.